Every year, the global supply chain discards 1.05 billion tons of food. That volume represents a direct $1 trillion hit to the global market. Simultaneously, the decay of that specific organic matter generates 8 to 10% of all global greenhouse gas emissions. I'm Alex. In this breakdown, we are going to look at how the world's most efficient logistics networks are applying Lean Six Sigma to convert these unpredictable acts of nature into solvable process variances. For decades, agricultural distributors wrote off biological degradation as inevitable shrinkage, a cost of doing business. But in a highly optimized, low-margin modern supply chain, accepting a massive volume of waste as an inevitability destroys profitability. Look at this diagram comparing a traditional factory with an agricultural supply chain. A manufacturing floor is a closed system. You control the ambient temperature, the humidity, and the mechanical inputs. Agriculture is an open-air environment. The variables fluctuate continuously from the soil to the cold chain transport. To manage this, operators rely on Lean Six Sigma. This methodology integrates Lean's strict focus on speed and flow with Six Sigma's mathematical approach to variance reduction. But standard Lean Six Sigma relies on historical logs and manual sampling. By integrating the define, measure, analyze, improve, control methodology, or DMAIC, with digital technologies like IoT sensors and artificial intelligence, the industry developed Lean Six Sigma 4.0. This framework eliminates what engineers call unused knowledge waste. Every transit route and storage facility generates thousands of data points. Capturing that unused data allows operators to trace biological degradation back to mechanical failures, recapturing profit margins and ensuring quality from the point of harvest to the consumer's home. This diagram outlines the DMAIC framework mapped directly onto an agricultural supply chain. It begins with the define phase. Operators map the exact value stream and isolate the voice of the customer. For perishable commodities, the customer's voice prioritizes two strict metrics: freshness and food safety. In agribusiness, the end user eating the product has different baseline demands than the B2B distributor moving the freight. Aligning a supply chain with programs like USDA Process Verified standards ensure specific, documented requirements for traceability are met at every transfer point. Next is the measure phase. Because organic material degrades rapidly, manual temperature sampling creates blind spots. Manual logs are obsolete. They must be replaced by continuous LSS 4.0 tracking tools. This requires specific hardware. Facilities deploy active cool containers equipped with automatic control units, Bluetooth low-energy temperature sensors attached directly to pallets, and integrated data loggers recording environmental shifts down to the minute. Precise, automated measuring is the absolute prerequisite. You cannot capture the true capability of a biological process if your data is delayed by manual clipboards. With real-time data collected, operations move to the analyze phase. A detailed study of the Egyptian agri-food sector demonstrates this. Researchers used Pareto analysis, a statistical technique highlighting the most frequent causes of failure, to pinpoint the exact root causes of food waste during transit. The visual evidence from the study revealed that the defects were entirely mechanical. They documented unprofessional handling, poor adjustment of boxes inside transport trucks, severe overstacking, and pallets left exposed to direct sunlight. To correct physical handling errors like these, operators initiate the improve phase by executing the 5S methodology: sort, set in order, shine, standardize, and sustain. This clears unnecessary materials, reorganizes loading docks, and creates strict visual guidelines for handling. They also implement rigorous first-in, first-out, or FIFO, inventory controls. In a perishable supply chain, failing to rotate older stock to the front of the line guarantees immediate product loss. Finally, the control phase sustains the improvements. Operators run regular supplier audits and integrate real-time telematics units using cellular networks. If a truck's refrigeration unit begins to fail, the GSM unit triggers an automated alert, allowing dispatchers to reroute the freight or fix the hardware before the temperature crosses the critical spoilage threshold. Executing this complete DMAIC loop turns an invisible, compounding biological loss into a visible, highly correctable mechanical error. To see how this translates to hard revenue, look at this data table for a packaging olives facility. Before intervention, the drained weight of packed olives fluctuated wildly. This variance caused severe deviations, massive rejection rates, expensive rework, and significant financial loss. By applying DMAIC, the facility stabilized the process. They reduced standard deviation of drained weight by 51% and the parts per million defect rate by 99.97%. This single stabilization saved the facility $228,000 annually. This methodology scales directly to the point of harvest. At Nature's Gift Banana Farm in Malawi, operators applied Lean Six Sigma directly to the fields. They deployed value stream mapping to track the exact route of a banana from the tree to the truck. They utilized the Plan, Do, Check, Act continuous improvement cycle and enforced strict FIFO protocols in their distribution. The operational outcomes were immediate. The facility streamlined its harvesting workflows, measured a decrease in the bruising rate of the fruit during handling, and established more efficient irrigation practices. Whether an organization is optimizing factory drained weight or preventing farm-level bruising, these tools yield measurable physical and financial salvage. We see the exact same viability across different commodity types. In the highly regulated meat processing industry, variance equates directly to wasted organic material. By deploying Six Sigma statistical techniques, one processing study successfully stabilized their cutting and sorting lines, eliminating 130,655 kilograms of trimmings that would have otherwise been classified as food waste. When you move from localized processing facilities to macro-scale global enterprises, you find these frameworks embedded in the corporate structure. Fortune 500 agricultural giants like Cargill and ADM operate massive multinational logistics networks. These firms do not leave process optimization to chance. They employ dedicated operational excellence teams whose sole directive is to deploy Lean Six Sigma frameworks across their global supply chains, auditing suppliers and standardizing data collection. At the Fortune 500 level, supply chain resilience is not about avoiding open-air disruptions. It is about engineering data-driven systems capable of controlling them. Implementing this framework is difficult. Academic research has identified 23 distinct challenges organizations face when attempting to adopt Lean Six Sigma 4.0. The first major pitfall is the double burden skill gap. Modern practitioners are forced to master both complex statistical quality tools and emerging digital IoT hardware simultaneously. To mitigate this, organizations must focus their capital on comprehensive capability building and rigorous employee training. Purchasing a new software dashboard is useless if the personnel cannot interpret the statistical outputs. The second pitfall is creating operational silos. Companies often confine Lean Six Sigma applications solely to their procurement or logistics departments, isolating the data from the rest of the network. This is solved by deploying end-to-end value stream mapping across the entire supply chain, ensuring that a temperature reading at the farm is visible to the processing facility downstream. The third pitfall is the most critical, a lack of top management support. In my experience, if the executive suite treats Lean Six Sigma as a temporary cost-cutting initiative rather than a permanent operational standard, the framework will fail. Implementations collapse when they are treated as localized software patches. They require a long-term, top-down strategic vision to survive the friction of actual supply chain operations. The agricultural industry is currently rebuilding its operational logic from the ground up. Massive physical loss is no longer classified as unavoidable shrinkage. It is a solvable process variance. This requires integrating Lean Six Sigma, Industry 4.0 technology, and circular economy principles, pairing IoT digital tracking with the strict statistical rigor of the DMAIC cycle. Executing these frameworks properly allows an organization to recover massive profit margins from the point of harvest to the consumer's home while cutting the environmental toll of global food waste. Understanding the theory is only the baseline. Deploying these methods in the field requires specialized, rigorous training. If you want to apply these tools at the level the world's best organizations do, formal certification is the path. At Six Sigma Development Solutions, we've trained over 4,000 practitioners across 52 countries to do exactly that. You can find a link in the description to explore our certification programs and operational excellence training to see exactly how these frameworks map onto your organization. The modern supply chain has no margin for unused knowledge. Where variables are constantly shifting, teams with the best data and the strongest operational discipline are the only ones equipped to control the outcome.